Alright then, let's get to bitwise operators. Java defines several bitwise operators that can be applied to the integer types long, int, short, char and byte. Okay. These operators act upon the individual bits of their operands. They are summarized in the following table. This is bitwise unary not. Okay, this is bitwise and then we have bitwise or, bit exclusive or, right shift left, right shift zero fill. Oh, left shift. Then we have bitwise and assignment. Then we have assignment zero fill left assignment. Okay. Since the bitwise operators manipulate the bits within an integer, it is important to understand what effects such manipulations may have on a value. Specifically, if it is useful to know how Java stores an integer and how it represents negative numbers. So before continuing, let's briefly review these two topics. Okay. So let me bring it in focus. Okay. All of the integer types are represented by binary numbers of varying bit widths. Okay. For example, the byte value of 42 is 00101010, where each position represents the power of 2 starting with 2 to the power 0 at the rightmost bit. Right. The next bit position to the left would be 2 to the 1 or 2, continuing to the left with 2 square of 4, 8, 16, 32 and so on. So 42 has one bit set at position 1, 3 and 5, counting from 0 at the right. Thus 42 is the sum of 2 to the 1, 2 to the 3, 2 to the 5, which is 2 plus 8 plus 32. All of the integer types except char are signed integers. Okay, char is unsigned. This means that they can represent negative values as well as positive ones. Java uses an encoding known as 2's complement. Okay. Which means that negative number are represented by inverting, changing the ones and vice versa. All of the bits, then adding 1 to the result. For example, minus 42 is represented by inverting all of the bits in this, then adding 1, which results in this, or minus 42. Okay. So Java also uses 2's complement. To decode a negative number, first invert all of the bits, then add 1. Okay. So we perform the same operations to get the original value. The reason Java and most other computer languages uses 2's complement is easy to see when you consider the issue of zero crossing. Assuming a byte value, 0 is represented by 000. In 1's complement, simply inverting all of the bits create 11111, which creates negative 0. Okay, this is negative 0. The trouble is that negative 0 is invalid in integer math. That's right. This problem is solved by using 2's complement to represent negative values. When using 2's complement, 1 is added to the complement, producing this. This produces a 1 bit too far to the left to the produces a 1 bit too far to the left to fit back into byte value, resulting in the desired behavior where minus 0 is the same as 0. Okay. And all ones is the encoding for minus 1. Right. Okay. Which creates negative 0. The trouble is that negative 0 is invalid. Right. Although we used a byte value in the preceding example, the same basic example applies to all of the integer types. Right, so because Java uses choose complements to store negative numbers, and because all integers are signed values in Java, applying the bitwise operators can easily produce unexpected results. For example, turning on the high order bit will cause the resulting value to be interpreted as a negative number, whether this is what you intended or not. To avoid unpleasant surprises, just remember that the high order bit determines the sign of an integer no matter how that higher order bits gets set. Okay, so the most significant bit to the highest order, yeah, high order bit, too far to the left, determines the sign. The bitwise logical operators. Okay, the bitwise logical operators and or XOR and NOT. The following table shows the outcome of each operations in the discussion that follows. Keep in mind that the bitwise operators are applied to each individual bit within each operand. Okay, 0 0 is 0 0 0 and NOT is 1. Okay, if they are 1 0, OR is 1, this is 0, this is 1, this is 0, 0 and 1, this is 1, this is 0, this is 1, and 1 1 1, this is 0. Okay, so OR, if both are, if if either one of the operands is 1, then we get a 1. If both operands are 1, we get a 1, and if both operands are different, then we get a 1. And here, if it is a 0, it gets converted to 1, and vice versa. Okay, so we talk about the bitwise NOT, also called the bitwise complement. The unary NOT operator inverts all of the bits of its operand. For example, the number 42, which has the following bit pattern, this becomes this after NOT operator is applied. Then we have bitwise AND. The bitwise AND operator produces a 1 bit if both operands are also 1. A 0 is produced in all other cases. Right. Then we'll go to here bitwise OR. The OR operator combines bits such that if either of the bits in the operand is 1, then the resultant bit is a 1. Okay. We move on to the bitwise XOR. The XOR operator combines bits such that if exactly one operand is 1, then the result is 1. Okay, if exactly one operand is 1, otherwise the result is 0. The following example shows the effect of. This example does not demonstrate a useful attribute for XOR operation. Notice how the bit pattern of 42 is inverted wherever the second operand has a 1. Okay, so this gets converted, this gets converted, this gets converted, right? Wherever the second operand is 0 bit, the first operand is unchanged. You will find this property useful when performing some type of bit manipulation. Okay. We have using logical operators, so I should write it down. Okay, all right then. Say bitwise operators, right? Bitwise operators. Let's make a directory bitwise operators cd to. Okay, let me make a new file. What is this called? This is called bitlogic. So we have bitlogic.java. Okay. Right. So we have this demonstrate the bitwise logical operators. Demonstrates bitwise logical operators. Then we have a class bitlogic and a function or right. So I create a array of string called binary. A string binary. Okay. Then I feel we have all the numbers 0 to 15. Okay. 0 0 0. Then 0 0 0 1. Then 0 1 0. And 0 0 1 1. 0 0 1. Sorry, 0 1 0 0. And we have 0 1 0 1. Then 0 1 1 1. Right. Oh, I forgot. Okay, we have 1 0. So I 1 1 0. Yeah, 1 0 1, then 1 1 0, then triple 1. 0 1 1 1. Then let me come down here. And then we have 1, which is basically 8. 1 0 0 1. Then 1 0 1 0. Then 1 0 1 1. Then 1 1 0 0. Then 1 1 0 1. And then finally 1 1 1. Right. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Incorrect, right? Triple 1. Did I ever hit a triple 1 0? Nope. Okay, so 1 0 1 1 0 1 0 1 0 1 1 0 0 1, and then I have to hit a triple 1 0 and then 1 1 1. Okay, there we go. Then we declare some variables. Yeah. Okay, so int a equals 3. This is equal to 0 1 1. Then we have int b equals 6. Int b equals 6, which is 4 and 2, so it will 0 1 0 0 4 and 2. Right, okay, then we take a OR. Int c equals a or b. So let's say this is 1 1, so we get 0 1 1 1. Right. Then we take an AND for d. Int d equals a and b, which is, let's say this is 0, this is 0, so only the second bit is active. Then we have Okay, so these corresponds to the index, right? So A or B, C we get this, and this is 4 2 1 7. So 0 1 2 3 4 5 6 7. Right. Okay, so that's what it is doing. Then we take D. D is then E is XOR, and E is A XOR B, which is C. Easy. This is a 1, this is a 1. So 0, 0, 1, 0, 1. Then we take an expression which is F. F is int F, and F is bracket not of A and B. Then we OR it with A and not of B. Right. Okay. So not of A is 1 1 0 0, and we end it with B. We get let me see. Not of A is 1 1 0 0. So these are 0. This is 1. So we get 0 1 0 0. The not of B is 1 0 0 1. So we not end it. So only this, only the last bit will be 0. So we get OR with 0 0 0 1, and when we OR it together, we get 0 1 0 1. Right. Then we have G. G equals not of A, and with 0 0 x0f. So we are knotting it with 15, right, with this. So we have not of A. Not of A is 1 1 0 1 1 0 0, and this is 1 1. So we will get 1 1 0 0, and now we print all the results. Okay, so system dot out dot print line, we have A. Oh, so A equals plus binary A. Then we have B equals B. Then we get A or B. Then we write A or B. A or B equals, okay, A or B is C. Then we have A and B. A and B is D. Then we have A XOR B is E. Then there's a complicated not and B. Then we OR it with A and not B is F, and then finally we have not of A. Finally, have not of A is in G. G. Okay, so let's print it out. Okay, system. Oh, my bad. Uh, Java bit logic. We get 011, 01011, 0111. Maybe I should. Um, okay. Hmm. Okay, this is right. And what can I do about it? Okay, so let me compile it again and run it. Ooh, dude, I did not think it would be that bad. Okay. Anyways, hold up. Let me try this. Well, yeah. Yeah, good the way you are. Yep, perfect. Okay, so there we are done with bit logic. So let me switch over. Um, so let me switch over to the book. Yeah, we move on to the second. So in this example, A and B have a bit patterns that represent all four possibilities for two binary digits, which is 0, okay, 00, 01, 10, and 11. Okay. You can see how the AND and OR and AND operate on each bit by the results in C and D. The values assigned to E and F are the same and illustrate how XOR works. The string array named binary holds the human readable binary representation of the numbers 0 through 15. Huh. In this example, the array is indexed to show the binary representation of each result. The array is constructed such that the correct string representation of a binary number value n is stored in binary of n. The value not a is ANDed with in binary in order to reduce its value to less than 16, so it can be printed by the use of binary array. Okay. Oh, okay. Because then it would be right, because if we have a is okay, 1 2 3 4, then we add two more zeros, and 1 1. Okay, this is actually A, and not of A is 1 1 1 1 1 1 0 0. Okay, so that's why we end it with this binary value. Alright, ये the binary array. Okay, then we have the left shift. The left shift operator shifts all of the bits and its value to the left a specified number of times. Okay. It has a general form thus. Here num specifies the number of positions to the left, number of positions to left shift the value in value. That is, this operator less than moves all of the bits in the specified value to the left by the number of bits positions specified by num. Okay. For each shift left, the high order bit is shifted out and lost, and a 0 is brought in on the right. Okay, so the high order bit is lost. This means that when a left shift is applied to an int operand, bits are lost once they are shifted past bit position 31. If the operand is a long, the bits are lost after bit position 63. Okay. Java's automatic type promotions produce unexpected results when you are shifting byte and short values. As you know, byte and short values are promoted to an int when an expression is evaluated. Furthermore, the result of such expression is also an int. This means that the outcome of a left shift on a byte or a short will be value int, and the bits shifted will not be lost until the shift past the bit position 31. Okay, okay. So the bits shifted left will not be lost. Okay, so all of the data is stored. Furthermore, a negative byte or short value will be sign extended when it is promoted to int. Thus, the high order bits will be filled with ones. For these reasons, to perform a left shift on a byte or short implies that you must discard the high order bits of the int. Furthermore, a negative byte or short value will be sign extended when it is promoted to int. Thus, the high order bits will be filled with ones. For these reasons, to perform a left shift on a byte or short implies that you must discard the high order bytes of the int result. For example, if you left shift a byte, value for example, if you left shift a byte value, that value will first be promoted to int and then shifted. This means that you must discard the top 3 bytes of the result if what you want is the result of a shifted byte value. The easiest way to do so is to simply cast the result back to into byte. Okay, so we have high order bits must be discarded. Okay. You want left shifting a byte shift, so we int I, okay, we produce I into 2 value, okay, I will be 64 and okay, because 256, alright. Got it. See in this example, if you can see indeed. Alright, so we have a byte with value 64 and a byte b, then integer and integer I. Okay, in I we say left shift 2, so simply we shift 64, right? 64 is 2 to the power 6, right? So we have for 8 bytes should be 0, then but this is a 8 byte, right? There will be a lot of bits in that. 8 byte 4 byte 8 integer is 4 bytes or 8 bytes, I don't remember. Maybe I need an I guess I need an eraser. Okay, so we have simply write it so let's say it would not be right. Okay, 64, so I'll know. See, this is 2 to the power 6 is 64, right? Then we left it by shift 2, so when we, so 64 2, it becomes 2 to the power 8, which is 256, right? So I say A is equals to this and I is equals to 2 to the power 8, which is 256. But 256 is not in the range of bytes because it is from 0 to 255. Therefore, it is again rounded, converted to 0. Since A is promoted to int for the purposes of evaluation, left shifting the value 64 twice results in I containing the value 256. However, the value B contains 0 because after the shift the low order byte is now 0. Its only one bit has been these are all are 0. Its only one bit has been shifted out. Since each left shift has the effect of doubling the original value, programmers frequently use this fact as an efficient alternative to multiply by 2. But you need to watch out. If you shift a 1 bit into a high order position, bit 31 or 63, the value will become negative. The following program illustrates this point. Okay. So we have this number int num shift by 2. Okay, so this, okay, it's an integer, it 8 bytes. I feel bytecode evolution of Java, and I feel like where are the data types? Second short program, block of code. Yep, integer is a 32-bit. Yeah, 4 bytes. Okay, integer is 4 bytes everywhere. 16-bit, short is 16-bit. Okay, integer is 4 bytes. Right. Okay, so we left shift this value 4 times, multiply by 2, then after a while, what is this? F. Okay, so the starting value The starting value was carefully chosen so that after being shifted left 4 bit positions, it will produce minus 32. As you can see, when a 1 bit is shifted into bit 31, the number is interpreted as negative. Okay. Shifted. Okay. So if we past bit 31, okay, then we'll study the right shift. The right shift operator shifts all of the bits in a value to the right by a specified number of times. Okay, so we have values these, and here num specifies the number of positions to right shift the value in value. Okay, value right specified by num. Okay. That is, the greater than operator moves all of the bytes specified in this value to the right the number of bit positions specified by num. With the following code fragment shifts the value 32 to the right by 2 positions, resulting in a being set to 8. Right. When a value has a bit when a value has bits that are shifted off, those bits are lost. For example, the next code fragment shifts out value 35 to the right 2 position, which causes the 2 low order bits to be lost, resulting in a being 30 set to 8. Okay, lost. Okay, looking at the operation, and these are lost. Each time you shift a value to the right, it divides that value by 2 and discards any remainder. In some cases, you can take advantage for this for high performance integer division by 2. Okay, it divides by 2 and that multiplies by 2. When you are shifting right, the top leftmost bits exposed by the right shift are filled in with previous content of the top bit. This is called sign extension and serves to preserve the sign of negative numbers when you are shifting them right. Minus 8. Okay. So when you are shifting right, the top leftmost bit exposed by the right shift are filled in with previous contents of the top bit. Alright. Called sign extension and serves the purpose. Negative number. Just binary. Okay. Then we go that it is interesting to note that if you shift -1 right, the result will always remain -1, since sign extension keeps bringing in more ones in the high order bits. Okay, so you cannot magically turn -1 into positive. Sometimes it is not desirable to sign extend values when you are shifting them to the right. Okay. It fill it with zeros. Okay, for example, the following program converts a byte value to its hexadecimal string representation. Notice that the shifted value is masked by ANDing with 00x to discard any sign extended bits so that the value can be used as an index in the array. Okay, so we AND it with this. Alright. 0x hex of B 4 bytes, shifted 4 bytes, and it with this plus hex B, and so we get F and then 1. Okay. Notice that the shifted value is masked by ANDing it with to discard any sign extended bits, so the value can be used as an index into array of hexadecimal characters. Masking sign extension x byte. Okay, so we have value which is 1 and 15. 1 plus 15 is 16. Okay. 1 plus 15 into 16. So 15 into 16 is, what is 15 into 16 is, I think 250, right? No, 16. Okay, 16 15 6 are 90, and 15 then the 150. 150 plus 90 is 5 plus 9, 240. 241. This is 240. Let me quickly check. Can quickly check that. Say X calculator. Okay. X decimal value. So we go F1. $241, right? As I thought. Okay. So we go here. Byte B is byte of 241. Then we go 0x. We shift it by 4 times, and with this, and then again. Okay, we shifted 4 bytes. Why do we shift it? Right, shifted 4 bytes. Because 241 is 241. Can I see the binary equivalent of 241? Right, sorry, let's spin this guy here. Okay, binary calculator. Yeah. Oh, but I even have this calculator which I can use. Yeah. Okay, so decimal 241 is, oh, okay. So we right shifted 4. Okay, so I have, alright, so I have 241 is 1 1 1 1. Then we have 0 0 0 1. Okay, we right shifted by 4, so we get 0 0 0 0, then 1 1 1 and 1. So this corresponds to F. Then we end it with 1 1 1. Okay, B, right. Right shift by 4 and end it with 1 1 1 0 0 15, right? And then we end with 15 again. B. Okay, is B right shifted right now? But I have not assigned B the value, so okay, I feel like I would have to do this. So I will quickly write out this bitwise operator. Let me make a new file called xbyte.java. So masking sign extension, masking sign extension. Okay, so when we right shift it, right, bytes are unsigned, right? We convert this value to an, okay, I still don't get, but okay, let me just write it out first. Right, okay. F plus x byte x static rx then okay, start at 0, right? So 0, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, and then F. Okay. Then I declare a byte B equals byte 0xF1. Okay. Equivalent of 240, 241 or 111 0, 0, 1. So we get this is 128, 64, 32, 16 and 128 and 1. Okay. Then okay, if I right shift it, right, okay, so system dot out dot print line p4, okay, and I just want to print p here. X byte -1 and -15. Okay, there's -1 and -15. Okay. Okay. Okay, so even with byte, it is -15. Okay. So because if I cast it as byte, nope. Okay, so bytes can have negative value. Okay, so because of this, it is hiding it as, okay, I can do that. See, 100 and 128. Let me do the calculation. Standard, we have -128 plus 64 plus 32 plus 16 plus 1 -15, right? Okay.